My name's Miriam.
My name is Myra, and this is our project problem for our Calc 1 workshop class.
So the problem states, consider the curve C given by the equation x squared minus xy plus y squared equals 9.
For number 1, this curve is composed of two distinct explicit functions of x. Uncover these two explicit functions of x, making up curve C.
So we're going to start off by explaining what explicit and implicit is. Implicit is a function in which one variable is not defined in terms of another variable.
And explicit is a function in which one variable is defined only in terms of the other two variables.
So we first need to understand that our problem is composed of two explicit functions. So we need to get the quadratic formula because that's going to give us two functions. First, we're going to get our equation and equal it to 0. And then, since we're going to use the quadratic formula, we need to solve for our variables. So A, B, and C. So A is going to be 1, B is going to be negative x, and C is going to be x squared minus 9. And this is because we're solving for y in respect to x. Now, Myra over here has the equation solved out.
Okay, so Miriam found A, B, and C. So now we're going to plug it into the quadratic formula. So this is the quadratic formula, and we're going to plug each into the quadratic formula, which, as you can see, it will simplify further to our two explicit functions, which is plus and minus. So this will be their two explicit functions once we finish with the
My name is Amdi Basid, and question 2 says, by use of implicit differentiation, part 2a said find dy dx for any point x, y on C. So what does dy dx mean? Dy dx mean we put dy as an function and we respect x. So for the curve, we have x squared minus xy plus y squared equal 9, right? So let's just put in terms of this as a function, or just put this as a 0, x squared minus xy plus y squared minus 9 equals 0. We could call this as a function as like f of x or f of y of x. We'd have to do that in this case. So we know this y is a function, and x is, we could differentiate x, so it's just going to be 2x minus, this is a bigger case, so we're just going to do it later on, but we're going to do differentiate to the first one, then y plus to the y to this one, plus times x. And y squared is a function, so we're going to do 2y dy dx. And minus 9, the derivative of this is 0. So that's it for this one. So we're just gonna simplify this more. 2x minus x to the differential of x is just 1 times 1 y plus, this is the same thing as saying dy dx. We're respecting x, y is a function, and this is x plus 2y dy dx. Now to the next part, we'll simplify it more. We're just gonna get the negative inside. It's just gonna be negative y minus x dy dx plus 2y dy dx equals 0. Okay, now we're gonna get dy dx by itself. So as you can see right here on the table, it says to find dy dx, so we're gonna put in terms of dy dx. So as you can see, negative x, this part I'm just gonna bring it down, negative x dy dx plus 2y dy dx, and take these to the other side. So it's gonna be negative 2x plus y, right? And now we're just gonna factor out this x, negative x, and this 2y, just to leave dy dx alone. So we're just gonna dy dx negative x plus 2y equals negative 2x plus y. So now we just divide this to the other side to just get dy dx by itself. Dy dx equals negative 2x plus y all over negative x plus 2y. So as you can see for part B, it says to complete the table. And as Zach did before, we have two functions from the quadratic, the plus and the minus. So for negative 3, we could use both of them. See, we have two negatives, 3's, and 2 zeros just for those two functions. And as I did before, the implicit dy dx, y is a function, dx respecting that, we're just gonna plug in these numbers to just get dy dx. Okay, so this is a long process, but it's really easy to do. So I'm just gonna do, for the functions, I'm gonna do with blue color, blue marker. So it says f of, this is f of negative 3, f of 1 over negative 3 is equal to negative 3 plus square root of negative 3 squared plus 36 all over 2. So we did this already on the calculator. If you want to solve this, it's just easy, and I have the answer already for this. So the answer is 0. So we just say f of 1 is 0 or y is 0. So x in this case is negative 3. So we all fill this one up. This one is going to be 0. So okay, now let's do it for the second function, where we just have a subtraction sign. So I'll do it here. So it says f of 2 of negative 3 equals x minus square root of negative 3 to the negative 3 squared plus 36 all over 2. So you could do this in a calculator. We used a calculator to do this, and we got the answer as negative 3 for this part. So let's just come back to the table, and it's going to be negative 3. Now we do the same process for 0 and 3. So I'm just going to do the same process, as you guys could tell. So I'm just going to do f of 1 again to the 0 equals x plus negative 3 to the 0 squared plus 36 all over 2, and that's going to equal to 3. And I'm going to do the other one and then fill up the table. F of 2 to the 0 equal x, or in this case x is, my bad, I forgot to put the 0 here. In this case x is 0 plus negative 3, 0, this is subtraction, 0 squared plus 36 all over 2. And the answer for that is negative 3. Let's just go back and keep on track. So don't forget, so 0, 3 for that part and negative 3 for this part. Now for the last two, we're just gonna do the same thing. So f of 1, and it's gonna be 3. So x 3 plus negative 3 to the 3 squared plus 36 all over 2. And you can use a calculator for this, and we already solved it. You could check for yourself, and that's equal to 3. And one more thing, f of 2 for the same input 3 equals 3 minus 0 negative 3 squared plus 36 all over 2, which is equal to 0. Now let's go back to our table, and our table we put 3 and 0, and as you can see this relationship, you can see that something is forming. So we don't spoil this, someone else will explain this later. So now we're gonna do dy dx. So right here is the function I found before for part A, 2a. Now I'm just gonna plug the same numbers. So see, as we found the y, that's why we did the other one to find the y. So in this implicit function we have x and y. We could just plug in these two numbers on this one, and we'll get the values for dy dx. So let's get started. Let me erase this part. So to find dy dx, as you can see, I found this function at first. We have x and y, right? Now we have the two x and y right here, negative 3, 0, negative 3, negative 3, 0, and 3, 0, negative 3, 3, 3, and 0. Now we're just going to plug it in to solve it. So first we have negative 3, 0. So this is the x and this is the y, right? So negative dy dx. So it's a negative 2x, in this case is negative 3, and y in this case is 0. All over x is negative 3 plus 2y is 0. So you could do it as we did it by a calculator, or you could do it by hand, but we already solved this. This is equal to 2. So we're just gonna go back to our board chart, and this is just gonna be 2. Okay. Now we do the same thing for the other 1, 2, 3, 4, 5. We do the same thing for the other 5. So dy dx for this one, we're going to use negative 3, negative 3. So x and y, dy dx equals to negative 2. In this case, negative 3 is x plus negative 3 is y, all over negative 3 plus 2 to the negative 3, and which is 1, which is negative 1. So we're just going to go back to a thing and just okay. And next point we're going to do x and y. It's going to be 0 and 3. So dy dx is going to be negative 2, 0 plus, this is y, and this is going to be y going to be 3, all over negative 0 plus 2, and this is y, right? Yeah, 3, and the answer, we already got this, is 1/2. So we're just going to put 1/2 here. So 1/2. So I use this board for the next 3 points. So we have 0, 0, negative 3. So as you can see, this is x and this is y. So dy dx. So we have negative 2, x is 0. So we just doing the same thing over here again. So this is going to be plus, y is negative 3. All over negative 0 x, and y is in this case is negative 3. So we will get the answer we already computed. If you want to do the calculation, you could do it as a calculation, and it's 1/2, same thing as the other one. So we have 1/2. Now we have 2 more points, almost there. Come on. x and y. So we have 3 comma 3. So dy dx equals negative 2, and in this case 3 is the thing, plus 3 is the y, all over x is 3 plus 2 y. And we already got that. It's going to be negative 1. So let's just put it over here. 1. Now we are at the last point, which is 3 comma 0, and this is x, this is y. I just put x and y just to not mix up, you know. So dy dx equals negative 2, and in this case x is 3, plus in this case y is 0, all over negative, in this case x is 3, plus 2, y is in this case is 0. And if you could compute this, this is equal to 2. And we're finally done with our table. And that's it for this part B.
Hi everyone, my name is Nitya Roy, and I'll be going over the last section of our project problem. So the last part tells us to find the highest and lowest point on C, and as well as the vertical and horizontal tangent lines. So in order to find it, we write y prime in terms of x first, as indicated here. And once we do that, we get y equals 2x. So negative 2y plus y, which we know is 2x, gives us 0. So if you remember, horizontal tangent lines occur when the derivative or the slope at the instantaneous rate of change is equal to 0. So that means we have to find the derivative and set it equal to 0, and wherever the derivative is equal to 0 is where we have a horizontal tangent line, also known as a maximum or minimum. And the way that we determine if it's a maximum or minimum is by using a sign chart. So now that we have found what y is, we're going to substitute y, which equals 2x, into the original equation and solve for x. So once we do that, right here indicated by the algebra, we end up getting that x equals plus or minus the square root of 3. And the reason why it's two answers is because it's two functions that's going to form this ellipse for us. So now that we have our two x values, we need to find the corresponding y value. So next we're going to solve for y. So we substitute x equals square root of 3 into the function, and x equals negative square root of 3 into f prime of x. And once we do that, as you can see through our algebra, we get y equals 2 square roots of 3 and y equals negative 2 square roots of 3, which gives us the highest point and the lowest point. Now, we know this is the lowest point, first of all, because it's negative, and we know this is the highest point because it's positive. But if you really wanted to double check, you could always just do a sign chart. So now that we found the horizontal asymptotes, let's move on to the vertical ones. So if you remember from 1800 or whatever previous math class you were in, vertical asymptotes occur when numbers or your inputs break your functions. So what that looked like previously, as you might remember, is when we had things in the denominator that broke our functions. So we know that you can't have a 0 in the denominator. So we take the derivative function and we take the denominator and we set it equal to 0. And whatever that number equals, we know that number is going to break our function. So this was our derivative function. We set it equal to 0, which just cancels out the. We set it equal to 0, which gives us negative 2y plus 2y equals 0. So we know that x is equal to 2y. So next thing we have to do now is to substitute x equals 2y into the original equation, and solve for y. And when we do that, as you can see through the algebra here again, we end up getting y equals plus or minus the square root of 3. So now that we know y equals plus or minus square root of 3, we need to find the corresponding x values of the tangent line, knowing that when x equals 2y, we have an undefined slope, which we will so when y equals square root of 3 and y equals negative square root of 3, we plug that into x equals 2y, we end up getting x equals 2 square roots of 3, as indicated here, and y equals negative 2 square roots of 3. So our vertical tangent lines occur at 2 square roots of 3, comma square root of 3, and negative 2 square roots of 3, comma negative square root of 3. Okay, so if you remember previously, when we used the quadratic formula in order to get our two functions, these are the two equations that we got. X plus the square root of negative 3x squared plus 36 all over 2, and x minus the square root of negative 3x squared plus 36 all over 2. So when you graph these functions, this is what it looks like. It's just that red curve that you see right there. You can ignore the points for now. I'll get to them in a minute. And when we graph the second portion of the graph, this is what it looks like, indicated with the blue, and altogether it forms an ellipse. So in order to find the highest point of the ellipse and the lowest point of the ellipse, we know that when we take the derivative of the function and you set it equal to 0, the derivative at that point has to equal 0. So when we set the derivative equal to 0 for this first function indicated with the red, we get this point right here, which is the maximum. And there's two ways to tell how the graph either goes up or down. One is by using the sign chart, or you can look at the end behavior of the function and plot some more points. But it's easier to do a sign chart. So when you take this function, you set the derivative equal to 0. This is the point that you get, and from the sign chart we know that it goes down on this side, and on this side it also goes down. Similarly, if we take the derivative of the second function indicated with the blue, and you take the derivative and you set it equal to 0, you get this point right here. That's your x, that's your y. And similarly, if you do the sign chart, you see that it goes up, and it goes on the left, and then it goes up on the right. So once you draw all the vertical and horizontal asymptotes on the graph, this is a picture of what you get seemingly. And the vertical and all these horizontal and vertical asymptotes kind of give you restrictions on as to where the function cannot exceed. So when you have the horizontal asymptote right here, you know the function cannot go above it. Likewise, when you have the vertical asymptote right here, you know the function cannot go past it.
Hi, my name is Zachary Salzgiver. I'm going to talk about the conclusion of this problem. From beginning to end, it was pretty demanding. We went from being told that we were given a curve, and it was composed of two explicit functions, and that right away kind of got our minds racing. We were thinking about it from beginning to end, how do we know? And so we didn't even read further in the problem, and then as we did, to try to think that maybe we can solve part B or part C or number 2. We got to number 2 and it had a table, and we noticed that on the table the x value had 2 inputs that were identical. And so as we thought about that, we went back to part 1 and we were talking about it, we were discussing it, and we were told that the curve is composed of 2 distinct functions. And our mission was to find these functions, and it took a lot of conceptual understanding to figure it out. But after we graphed it, it was an ellipse. And so therefore, it had 2 mirror outputs. So for every input, instead of having one unique output, we had 2 unique outputs. And that makes sense because we're given 2 explicit functions. So we used the quadratic formula to solve our curve for our 2 explicit functions, f1 of x and f2 of x. The next conceptual issue is finding dy over dx, or y prime. We didn't know at first that the functions f1 and f2 of x should be derived, but we were given a huge hint by the directions by use of implicit differentiation, where they tell us that there's more than one variable, one which is a variable or an independent input, and the second is an actual function. So then we knew that we had to actually derive the curve itself implicitly. Lastly, which Nietzsche's going to explain, or already has, the vertical and horizontal tangent lines were required to know and understand the functions, but not only the functions and how the graph's supposed to look, but what these functions provide, what these equations provide. So if you think about it, we have three equations. We have f1 of x and f2 of x, and then we have the derivative. And so with f2 of x, and I'm sorry, f prime of x, dy over dx, it tells us the slope. So the inputs are the outputs of the derivative are the slopes of the function. And so to find the horizontal tangent line, we had to find when that function was equivalent to 0. That was pretty simple. That one we knew. And then for the vertical tangent lines, it was a little bit harder because all we knew is that it had to be undefined. But we didn't have any type of understanding, like no clues at first. What would break our function? And we kept looking at the curve, and we kept looking at the curve, and we were like, no, it doesn't make any sense. So finally we realized that, yet again, we have to use the y prime function. I mean, it should have been pretty obvious, but it wasn't at first. And so I believe when we went back over everything, it was when x equals 2 root 3 and y equals root 3. And then just the opposite, like I said, this is an ellipse, so for every output should have a mirror image. So those were the conceptual issues, those were the things that made it hard, but I think the problem was very well constructed. I think that we all agreed on that. And oh, one last thing, the quadratic formula. It kind of screwed us for a little while. But we ended up working it out because once we realized that we were solving for y and that we had to put things in terms of x, it made it perfect sense because we were given 4 terms in our curve, not just 3. And so typically in 1800 or in 1050 when we used the quadratic formula, we were solving things that had 3 terms that just weren't factorable or that were too hard to factor quickly. So it was actually quicker to use the quadratic formula. In this case, it kind of made sense because after you remove the y term, you just use the coefficients like any other time. So anyway, my name is Zachary Salzgeber, and we presented the project problem. Thank you for your time.